Hi, everyone. Welcome to 129 Stanford MedAI Group Exchange session. This week, we have Waqas Sultani from Information Technology University in Pakistan here with us to talk about their work on large-scale multi-microscope datasets. Waqas is an assistant professor at Information Technology University and a member of Intelligent Machines Lab. His main areas of research are computer vision and deep learning. He has been awarded the Google Research Scholar Award in 2023 and Facebook Computer Vision for Global Challenge Research Award in 2019 for development of low-cost solutions to disease detection. Before joining ITU in 2017, Waqas obtained a doctorate from the University of Central Florida under Professor Mubarak Shah. Waqas, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions? Can we interrupt you in the middle, or do you have designated breaks in your talk, or would you like to take questions at the end?
Okay, so I'm audible?
Yes, you are perfectly audible.
First of all, really thanks a lot for the opportunity and giving for me the opportunity to find the presentation. So I think I would prefer to take the question in the end, so that I can complete the what I want to say, and then yeah, this is my preference.
Okay, thank you very much, Waqas. So everyone, let's hold off on your questions until the end of the talk, and then we can discuss with Waqas. Waqas, please start your presentation.
Okay, so as Amara has told you that I will be talking about our recent work about large-scale multi-microscope datasets and the related challenges. So I would just like to take the opportunity to introduce our group. So we are basically from Intelligent Machine Lab. We are 2 faculty members there. So the work I'm going to show you is actually done by lots of other people, including me. So I have emotionally, and then we have few students. So we have been able to publish. We have actually pure computer vision guy. So we mostly focus on like CVPR, ECCV, and AAA, ICRA, and all this stuff. And also we publish sometime in MICAI. And these the papers, the research work that I'm going to show you is our recently published research papers in MICAI 2024. So in our lab, we work on the different kind of stuff, but I'm going to talk about the medical imaging analysis. And the work that I'm going to present is actually funded by a Google Research Award last year. And the malaria work that I'm going to present will be funded by Google Research, like Facebook Research Award stuff. So, so the ultimate goal, what we want to achieve here is that given the image, and they are the white blood cells, we want to predict, we want to locate and classify the type of the white blood cells. For example, in this case, we can say myeloblast, myelocyte, and the neutrophils, and then there's a none here, and then so on and so forth. Similarly, if we are given with the image which contains malarial cells, so we should be able to detect, like for example, this is trophocyte, one of the stages of the malaria. This is ring stage, this is Schizon stage, and gametocyte. Just to confirm, you can see my mouse, right?
Yes, we can see your mouse.
Okay, that's fine. So this is problem. This problem is basically given the image, we want to detect the object of our interest is called object detection. So Amara has told me that the listener will be of diverse background. So I will have a couple of slides about the object detections, some basic slides, so that we are on the same page for the rest of the time. So in the computer vision, like the object detection means given the image, you want to detect object of interest, like here's a car and the bus, the person, and like that and that. So, for example, and one of the basic metric that whether you detected the object correctly or not is that given for example, the image you want to, with the ground truth, you have some predicted box. So you find the IOU, international intersection over union. And if this is greater than your threshold value, then you consider that it is a correct detection. And if the class and the IOU is greater than some threshold, then you say that it is a correct detection. So this way you evaluate your object detection model. So there's lots of methods have been published, which is very some of these popular, like histogram-oriented gradient. Then there came the deformable part models, and then the selective search method, which actually reduce the location where you want to detect objects instead of sliding window. And then there's a paper by 2 years back. So this shows that this actually there's a huge increase in the detection and the classification accuracy of object detectors. And the most like exponential increase comes definitely comes after 2015 with the 14 with the introduction of with a large scale use of deep learning models. So these are the some of the examples. So we want to apply the same stuff like object detections to the medical imaging, like the malaria and the cancer cells and the similar other like white blood cells, normal and abnormal, and but they have their own issues and challenges. So, for example, let's talk about malaria first. So the malaria is named as a disease of poor. So basically, it doesn't. The people in the rich areas are not mostly infected by malaria, and the reason is that the it happens due to the mosquitoes, and the mosquitoes happens in the tropical and subtropical regions, and the regions that have poor sanitary conditions. So there's like still there are 2 to 6 million cases annually, and for around 400,000 people died, and 67% of children. And the malaria, although there's lots of death, but it can be easily detected. And if the early detection can happen, it can be easily purified. And one of the gold standard for the malaria detection is that you have a microscope, you put the blood smear slide under the microscope, and you detect the cells. So just for information, there are more than 3,000 species of mosquitoes, and out of the 400 species of Anopheles mosquitoes, only 60 carries plasmodium. So the plasmodium is actually the parasite which causes the malaria. And just again for your information, so the malaria does not happen from person to person. So the actually person get infected, then when the healthy mosquito come in contact with that person, he become unhealthy, and when that unhealthy mosquitoes bite another person, he also catch that malaria. So it means that if the person who has the malaria, he is taken out from that community, then you can stop that process. And that's why there's a lots of others very simple stuff like the simple devices are invented, like you can put the person in the room, you don't allow him to go out so that other person don't get infected. So, so this is a simple for the medical doctor. It's very obvious thing what I'm showing you, but because we have a diverse background, so here, so this is a simple peripheral blood slide. So it's kind of small mirror stuff at the plastic stuff. You put a blood dot here, and then you put it into methanol, and then you after some time, well, 15 minutes, you put under the microscope, and then you see the malarial cells and all the other, I mean, white blood cells and the red blood cells. So here we actually, some of our students, they want to have their picture, so I took their picture and they were happy for that. So they were actually, in the lab we have multiple microscopes, and so in the bottom they are actually, we are in the some laboratory in the remote areas in Pakistan, and obviously we have medical doctors. So you're working closely with the major diagnostic lab named Chuktai lab in Pakistan, and they have lots of data of malaria and cancer, and we are actually in very close collaboration with those doctors, and they actually help collected this data, and we actually these guys are just we just refine that data with the help of that. So those doctors, the medical doctors which actually have experience more than 20 years, actually they annotate the data. So this is one of the image that we have. It's not very good quality, but just for the visualization purpose. So here are the red blood cells at 100x, and these are the 400x, and these are the 1000x. So basically, you are looking at the image at the cells at the 4000 time resolution, and the gold standard for the malaria, because you want to look into the cells to see the structures, is to have the 1000x. So here are some of the examples that of the different malaria cells that we have captured in our data set. So the top row, you can see the healthy cells, And the second row, you can see there's a ring appearing in the cell. So this ring is actually has very nice shape, and this is indication of that some the cell is going to be destroyed soon. And then they happen the trophosal stage and the Schweizern stage and the gametocyte. So these are the 4, 5, 6 stages of the malaria. And whenever and the end of this stage, actually, our cell gets destroyed, and we lose that white blood cell, red blood cells. And actually, this happens if it happens continuously. We're going to lose our red blood cells, and that's why we become weak, and and we can die. So our goal of this research was to detect these cells among the healthy red blood cells. So these are some of the examples where in the right you can see here there are lots of other noise and the platelets and other noise due to the noise in the slides, noise in the cells. You want to avoid those as well. So when we started this research, we started with a very basic architecture. We obtain an image of the simple with a very good quality microscope, actually that doctor has that microscope in the Central Paramedical College in Pakistan, Lahore. So and we have the unit, and then we actually segment each cell, and actually we get the annotations each cell. So we have lots of cells. We train a simple convolution neural network so for to classify each cell whether it's normal and abnormals. And if the cell is classified into the abnormals, we further go to the second stage and classify them into the 4 stages. And also again we have the one privilege to have it here, the healthy cell again, so that we can have this. So we this is very simple network, and it works recently well. And we make a small app, and given the image, we load that cell, and this is ResNet 50 simple classifications going on, and we can count the number of malarial cells, and also we can show the doctor which actually cells we are showing them is a malarial cells. So this was something which we shared with the doctors here in Jagdalp. So here you can see that we not only actually because we not only show the count, we also show them exactly the cells which are showing them the malarial cells. And actually when we show the doctor that we are saying that this image have these number of cells, and then we also show them those cells, so this increase the confidence from the doctor that this thing is really working. So then what we did is that we collect lots of images, and then we stitch them together. Stitching was not that perfect, but it's recently well. And so we show them, we make a large panoramas, and then we do the classification. So this thing actually is very useful for doctors, for according to them, for the medical students, to teach the doctors like to show them like how this slide look like, and where is what the malarial cells and how it looks like, and all this stuff. Although because usually they do the practice manually, if they don't have scanner, which is very costly, so they don't have no other way to train the doctors. And also they can use this during the exams. They mentioned that to provide them these images so that they can test the doctors during the exams, that to find out the specific cells, and name them and classify them. So it was a very low cost, because we just use a microscope, put some mobile camera, stitch the images, and do the classifications. So, but when we actually collected this data set, and it was also published, so we realized that uh, the data set was captured by a very, I mean, good quality, high cost microscope. And so we again thought that maybe we are missing again this basic stuff. So the malaria is actually the disease of the poor, and that in the developing countries, the people observe poor health due to what we think is the main 3-4 reasons. One is that the expensive medical instruments are not available. Expensive means like even for some remote areas, getting $3,000 to $4,000 microscope is a luxury actually in several places. And also there's a lack of doctors that who can spend sufficient time to analyze the outcome of those instruments, because there's a huge unworkable ratio between the doctors and the number of the patients. So, and also most of the time in the developing countries, we don't have digitized data because they cannot afford. I mean, if they can afford expensive Microsoft, how can they can explore, afford $100,000 scanner of the whole slide images? So there's no digitized data. So we thought we try to enable the low quality microscope to works well, to works better. So what we thought that we should collect the data set with a multiple microscope so that we have the low quality microscope and the high cost microscope together. And then we can try to make it efficient, which means that the doctor usually have to go to the 1000x resolution to analyze the malaria. And that cell, that location is very time consuming, that lens, because this is called oil immersion lens. In order to see in details, every time the doctor has to put some oil there and then visualize that. And whenever he moved to new location, he have to clean that oil, put it oil again, and then so it's very, very time consuming. So instead the 400x, the 40x, which means like resolution, which sometimes we call it 40x. 40x means 400 times resolution. So you can have if you can identify malaria at that resolution, it will be very easy. So basically what we did is that we got two microscopes. One is Olympus C extension, which is more than $3,000, and otherwise is a very, very low cost microscope, which is around $180 microscope from here in Pakistan. So this was the work that I'm going to summarize in a few minutes, is actually got published in CVPR 2022. So here is the thing. You can see that the left, you can see the images which were captured by high quality microscope, and the right you can see the images which are quality by the low quality microscope. And in the between you can see the cells which are captured from the dome microscope. So the low quality microscope has smaller field of view. The has a blur view as well, and the knobs are not very good. So the doctors are not comfortable with the low quality microscope because this not a good quality. So we ultimately, although we want to collect the data from the low quality microscope, we have to use the high quality, high cost microscope as well, because we ultimately want to get the data annotated from there, because doctors are comfortable with a high quality microscope. So we have to collect the data from the high quality microscope, get the annotations, and then transfer those annotations in the low quality microscope. So here are some of the examples in our data set. So we have, so this is exactly the same patch across 100x, 40x, and 1000x. And left, you can see that image is in the left column, you see the images from the high quality microscope, and the right side, you see the images on the low quality microscope. So there are drastic difference between the details that you can see on the microscope. So our goal is to train the model from the left side and test the model on the right side to get it working on the low quality data. So just to give an idea, so the 100x, if you're looking at this red box, so 400 is red box like this, and 100x are this red box like this. So these are the cells. And so we're looking at actually few millimeter distances. So if you're not a medical doctor, or if you're just computer scientist and you want to collect the data, a very minute touch with the knobs, the microscope, and you will lose the cell, and you will never be able to find it. It's very, very difficult unless you have the tracking going on, and which actually we did. So when we started collecting data, it's very, very hard to get to know exactly where is that cell is. So what we did is that we have this setup. We have the microscope, then we have the two cameras, 1 and 2 here, which was actually, these cameras are looking at this scale, the microscope, and this scale, the two scales, horizontal, vertical axis, and then one camera is above the microscope. So when the doctor was finding out the malaria, and she said that, okay, I found that malaria cell, you can take the picture. We press the button, we take the 3 pictures at a time, one picture of the actual image, one picture of these coordinates, and these, for each image we have these coordinates, which means that even after 1 year, we have the same with the same slide. We can go to these coordinates and we can find exactly where that specific cell is now. Actually, it should be at the same place, but we really want, if we want to get the image again, or we want to see the locations, so we actually capture the XY coordinates of the microscope. By the way, these coordinates actually vary from microscope to microscope because they are not 100% identical. They have their own I mean, calibration noise and all this stuff. So what we did is that once the doctor gave us the patch, we went to she actually gave us the slide, and she found the patches and gave us that, okay, this is a slide, and these are some of the images that contain malaria cells, and she annotated for us. Now I can go with you to find the malaria cells at the 400x and then 10x and then across the microscope. You have to do yourself. I can definitely confirm, but you have to do yourself. So what we did is that given the cell, we actually tried some deep learning method, doesn't work out, and then we tried this simple SIFT based matching, and it really works for these specific images. So we compute the SIFT features and then they do the matching, and then they find the patch here. And then basically, if you go to the you change the resolution like 40x from 100x to 40x. So we basically, this patch which was in the original image here, when you go to the 40x, it should be it is somewhere here. It's because this is because of the calibration noise. You don't find the exact patch when you change the scale. You change the scale, you find it somewhere else. So what we did is that we used the, again, simple KLT based tracking, and it's a real-time tracking. So we actually, once we know this patch contains the field of interest, we actually, now we move the knobs of the microscope, we can keep track of these cells, and then this way we can keep capturing the data. So these are some of the comparisons with the other existing microscopes. Existing data sets. So we believe our claim is that we have one of the largest publicly available malarial data sets, which is across microscope, multi magnifications, had the bounding box penetration also, and this data set is publicly available. I think I will be sharing this whole slide with the Amara, and she can share with everybody. We have put the links of the code, which and also the link to the data set we have, and anybody can use it. So to generate the baselines, we train different networks. So FCOS, Latina, YOLO, and FastRSN with the different resolutions. We train the 400x and 100x, train 100, and we tried all these combinations to find the best working or among these four, which one is the working best. So in that experiments, we found the FastRSN actually working well, giving us this one accuracy. So for the rest of the experiment, we continue with FastRSN. So we actually wanted to train the classifier on the high quality microscope and test in the low quality microscope. So which means that this is a problem domain adaptation. So what we did is that we have the high quality microscope images and the low quality microscope images, and that we train a cycle GAN, and then we from the high quality images we generate intermediate low quality fake images. So we converted high quality images to the low quality microscopic images. And then what we did is that we use the partially supervised domain. Partially means that we assume that we have corresponding pairs from the low quality and high quality microscope. So and then we use some constraints. So the constraint was microscopic or the data specific. So for example, one of the constraints was that so the high quality microscope has a large field of view, so usually there are a large number of objects detected. The low quality microscope has a low number of has a small field of view, so has less number of objects detected, less number of objects. So this is we use the ranking loss, which means that if the number of objects detected in the high quality are must be greater than the number of objects detected in the low quality microscope. Other thing is that we use the triplet loss, which is standard loss that we use, is that the images coming from the same from the high quality and the low quality microscope, since they're coming from the same areas, so they should be close to each other as compared to the patch which is coming from any other area. So this is the constraint we use, and we actually integrate into the faster RCN, and we observe that it helps a lot in improving the classification accuracy. So we train the model on the high quality microscope, test on the low quality microscope. We get just 17% accuracy. Then when we use this cycle GAN, we get improvement, and then we use these losses to get much better results. So basically, our ultimate goal is from the training from the high quality microscope and test on the low quality microscope. And so this is a domain adaptation problem. So we collected the data set, and then we observed that there's an issue in training and testing. So this is something that the method we come up with. So here are some of the results that showed our, like, these different color boxes are show the different classification results. So these are the images from these are the results on the low quality microscopes. So when we are actually working with the malaria, and we went to the head of diagnostic lab, like there's a guy, Umar Chuktai, and we asked them, do we have very recent work? We showed, I mean, we are getting very recent results of the malaria. So he said this, why are you working on the malaria? So he says, good problem, but exactly same techniques can be applied to leukemia, the blood cancer. Why don't you want to work on that? We thought, yeah, this is this is a good problem to work on. And he said, we have a lot of data. Why don't we work on that? And then we started working that. And then before working, we applied for the Google Research Award, and thanks God we got that. So we got a funding, and we got a good problem to work on, and we got a data, and that's good. So then we started working the leukemia, and we applied exactly similar data collection technique to collect the leukemia and for the blood cancer, which is leukemia. So the leukemia is one of the 10th most frequently diagnosed cancer, and this is one of the leading cause cancer under the age of 10. And once happen, it's a quick it diverge quickly. So, and there's a loss of death every year in the different areas of the world. So this is I'm going to talk about this was the oral presentation of last week. I mean week before last week. A large scale multi-domain leukemia dataset for white blood cell detections using the morphology exploration. So basically, what happened when you have a blood cancer? So you have some initial symptoms. The symptoms are usually not related to cancer. You have emotion, you have a fever, you have sickness, and all this stuff. They go to the doctor. The doctor do the your CBC, and do the like your peripheral blood analysis smear. And then if he wants, he can go to the flow cytometry, and then the bone marrow aspiration, and then the molecular testing, and so on and so forth. So one of the crucial step here is which is very in the very start, is peripheral blood analysis, which means that you have the blood sample, you put it under the microscope, and then you analyze it. So we work on this area, and but we observe that there's a few challenges here, because similar to the malaria, for the leukemia, you should have a decent level of expertise to detect and properly diagnose the white blood cells, to classify the white blood cells. And there's a lot of papers in this that there's a false positive and false negative is too high for the medical doctors. So obviously, computer-aided systems can help, because they can increase the efficiency, they can increase the productivity, and they can data management is easy. And obviously, they not always, but many times they provide the improved accuracy. But in order to work for the computer-aided system, because we want to work in the real world situation, it must be trained on very large data set. And the data set should be diverse. The data set should be captured under the different lighting conditions, under the different resolutions, under the different microscopes, under the different cameras. So it should be diverse enough so that the model trained on it should be generalized and works very well. Second thing, during the testing, it have to work on the different set of devices, which means that at least during the training, it have seen some kind of data diversity in form of equipment so that it can be deployed easily during the testing. Third thing that we observe, and actually we talk to doctors, sorry, as well. Third thing that we observe, that most of them doctor don't trust this AI stuff. They say that this is just making you are just making it up. So we thought that we should provide some kind of reasoning to the doctor, so they start trusting this thing, that that this is really meaningful. So one of the stuff that we observed, that we talked to the doctor, and they actually, one of the doctor, he was head of department. He was kind enough that he gave us a medical book, and they have the morphological attributes, like, so he told us that when we physically analyze these cells, so we see whether it has a nuclear chromatin, whether it's versus shape, whether the size is, the white blood cell is big or small, whether it's cytoplasm basophilia, whether cytoplasm vacuoles, something like this. So these are 7, 8 attributes, or more than that. They look, and then based on that, they decide whether the cells is a myeloblast or neutrophils, like that. So we told them that, what if we provide, in addition to detections, we provide these attributes, and we tell them that, okay, we tell you this cells is neutrophil, but we also provide 7 reasoning for that. And this reasoning is not in terms of like deep learning, it's reasoning instead of in front, the reasoning is for the doctor, that the doctor can see that, okay, your model is producing this stuff. And actually we make an app for this demo, and the doctor first answer to question to us, is it genuine, or you're just making it up? We say, no, you give a random slide, it will really works. So again, we actually go to the literature, we survey all the available datasets, and we observe that some, like majority of them, either single or 2 type of leukemia, none of them was across microscope. So there are some one dataset that have multiple microscope, 2 microscope, but there's no correspondence between 2 microscope. Again, there's a mostly of the single cell. They just capture single cell, like a very popular data set, for example, IDB2. They just have one big cell in the image. Then there's in the image wise, sometimes they don't have localization. All of them are of the single resolution. They don't capture the multiple resolutions. And then the number of classes are 2 to one of the data set have 15 classes, but rest there are several other limitations. They just capture one kind of AML. And only one of the paper is first published in last year in Europe. It has some morphology, but it just captured the normal cells. So we observed there's a lot of limitations. So we try to address all these limitations in the new data set. And so in our data set, we have 28,000 images captured with using the low and high quality microscope. They are one-to-one correspondence between the different resolutions in the different microscopes. And we have captured the data as 3 different resolutions, 2 different cameras. So we have a high quality microscope camera, low quality camera, and then we capture the data with using the simple mobile phone as well. And we have around 88,000 cells and 14 classes. And again, we believe this is one of the largest data set on the leukemia, and it is also publicly available. So what we did, we actually did the same thing. So we actually have the 2 microscopes and that we used before. And then we have, but this time we have the multiple cameras. So we use this mobile phone for this microscope. So we attach mobile phone here. And then we have a good quality, it's around $300, $400 camera here. And then we have around $50 camera, which is low cost, because we want to capture the quality low cost data. So we also have the low cost camera. We don't want to put the high cost camera on the low quality microscope. So we have the mobile and the low quality camera here, with a mobile and high quality camera here. So we have the both setup. So this is again we have the four thing here. We have this camera in the mobile phone here. And then we have the two cameras which are capturing the axis so that we know exactly where the doctor have found that cells where the images has been captured. Because sometimes in the runtime when you taking the image, sometimes the quality is not good. So you want to again take that image. So so that's why we have exactly to know that these coordinates. So we can anytime we can go back, put the slide there, move the knobs, and then take the picture again. So these are some of the setup. So again, we as was shown before, so we had the low quality camera. So this is a C2. C2 here means this special purpose here. So we and the C1 is a mobile phone camera. So we have the high quality microscope. We take these images. So these images are captured by cameras. So you can see that there's a difference. So this image is smaller because low quality microscope has low small field of view, and high quality microscope have captured the big area. And then even with the same mobile sensor, we can see that there is a difference because the difference of the lens, we have the different quality images. So this is the same images captured at 40x. These are same images captured at 10x. And then we actually get a notation because the doctor, we showed them all these images for different slides, and they told us that this C2 and 100x is the best quality images. And we got the annotation on these best quality images because we don't want to get something annotation on the low quality images. And then we transfer these annotations on all these locations to the different areas. So, for example, we have we have lymphoblast, myeloblast, neutrophil, basophil, eosinophil, lymphocyte, chromocyte. I don't know, a lot of stuff. To me, it's A, B, C, D, E, F, G, all the classes. So, but doctor knows better. So, monocyte, monoblast, and all this stuff. So, yeah. So these are the 14 classes, and the none class is very important because there's a lot of cells where doctors are themselves are not confident whether which kind of cell it is, or whether this is the cell or this is something obviously these are white blood cells, but whether it's normal or abnormal. And even with the multiple doctors, they are not sure what is this. So I mean, they're not sure of the class. So we put it as a non-class. And so, for example, this is cell is a myelocyte in this cell, and then we have these attributes. So she told us this cell size medium to large. The nuclear chromatin is coarse. The nuclear shape is irregular. Nucleus is uncontiguous. Cytoplasm is abundant. Cytoplasm basophil is moderate, and cytoplasm nucleus is absent. So we have here is a multiple attributes. Like for each attribute, they have multiple options. And then they selected, so this cell has this thing. So what we want to do ultimately predict that given this cell, this is a myelocyte and this has these attributes. So what we did is that given the microscope, we actually get the images, and then we have used the standard detectors. In our case, we tried again different detectors. YOLO V5 worked the best in our data set. So we capture the data set from one thing is that standard like object classification loss and the bounding box loss, and then we capture picture that we get the multiple resolution features. And for each multi-resolution features for each cells, and then we can get into those features and use a small neural network to get the attributes. So we actually predict along with the standard object loss and the classification and boundary loss, we also predict the probability of each attribute. So but we observed that and we actually have gone through the different reports that the doctor wrote. So one interesting thing that we observed, that the most of the text remains the same. Only the few keywords they are changing. So since we have attributes and then we have the class, so we thought we can generate a text. So it's not a text generation in the true sense, it's just a keyword generation. So all of the text remains the constant. So these colored words are actually what's the prediction of a word, and this we can actually in addition to the visual images, we also produce this kind of text for the doctors. For the experimental purpose, we basically tried again different networks, and we tried on the different microscopes and different resolutions. And like SCM is high quality microscope with a 100x resolution and the C1 camera. The C1 is basically the mobile camera, and the C2 here is this high quality camera, and LCM is the low quality microscope, 100x, and mobile camera, and vice versa. So we tried actually the 4 types of networks, and in our case, so the YOLO works better, and that's why we actually, in the previous slide, I showed you that you use the YOLO, and then we change the architecture a little bit to that it can predict the attributes along with the simple detections. So other thing that we observe, because we are predicting extra information, which is attributes from the YOLO. So we observe that if you use the standard YOLO, we have 26.3 MAP. If we use the attridate in our case, that along with the detections, you also predict attributes, you get some better accuracy. So yeah, so these are some of the results that our method have done, and as you know, so the YOLO is already works real time. So this actually the results were actually predicted real time. So so these are the results, and some of the qualitative results, obviously. So since we have the different domains here, for example, this is a one microscope, and the other microscope with the different challenges. We got different resolution, different scaling, field of view, and low quality and all this stuff. So we basically also generate the baseline results for the domain adaptation for the leukemia. So these are some of the baseline results. We didn't contribute some method here. This is just the standard baselines. We run 2 baseline results to see how are they performing. So there's a huge gap here for the performance wise. So for I mean, it's just very low, small numbers. So this is just a start, and anyone you can try it out. So these are some of the contributions. I can share the slides later on. You can see whenever you get time. So one of the challenges that we observe, as you might have guessed during the presentation, is that it's very, very hard to get the annotations. So doctors are willing to get the annotations on the high quality microscope, or for the low quality microscope, we have done it ourselves and then get it verified from the doctors. Obviously, we have the one-to-one cross models with the exact patch. So next thing we thought, maybe we can try out a few short domain adaptation, which means that so the domain adaptation means we in the standard domain adaptation, which is the unsupervised domain adaptation, we have all the details and the object detections, annotations for the training, but we we assume that we don't have any annotation for the testing dataset. For the few-shot domain adaptation, we assume that we have few examples which are annotated, and for these are the target domains. So the source domain and the target domain is, for the source domain we have all the annotations. For the target domain we do have only few. So which in our case, this looks feasible because for the source domain, the doctors were willing to annotate because there's a high quality microscope, they can easily see it. For the low quality microscope, they were not willing to annotate the data. So what we say that, okay, you can annotate at least few images, and we can use that for the better results, because unsupervised domain adaptation works pretty bad. So again, so the challenges remains the same. So with the high quality microscope, we have the very good quality images. For the low quality microscope, you miss the details, and for the same images. And again, the second thing is that the data that we collected ourselves, and also there's a publicly available data set, Rabin WBC. So they have extreme class imbalance, and this is not the some limitation of data set. This is actually the reality when you take the images. So you can usually we collected lots of data set, lots of patient slides, and we observed that this Streisand actually occurs Streisand stage occurs I mean only few cells. Most of the cells that we found out were the ring stage, and then the trophocyte, and then the gametocyte, and in the foundation of Streisand. Perhaps in the data set we have just maybe 12 or 14, I mean less than 20 Schweizern. And similarly will happen with the WBCs. So what we propose here is that we thought maybe we should try something to, because we have the target domain data and with the source domain data, we can try something to have some kind of class imbalance, class for the better training of the data set model. So given that we have the source and target, and we have these are different distributions of the gametoside, and trophocyte and ring stage. So we try to balance this distribution. So what we did is that we from the source domain, we actually get this. We have the annotations because we assume that we have the fully supervised data from the source, not from the target. So because target is only few short, so we get this, crop this cell, we actually do some Gaussian blurring, and then we use some random intensity variations and put that cell somewhere in middle. And so we put that cells somewhere in the image, in the another image. And we do the same for the we crop all the cells, we count the distribution, and we try to balance the distribution. Similarly, what we did is that we had the target image, we get the annotations, and then we distribute over the source domain, and we try to balance these distributions. So this is something. So this is the original source, and these are the cells which are augmented. Similarly, these are the original source. These are the few cells which are either coming from the low quality microscope or the source domain. So what we did, given that we have a few targets in the source domain, we applied this augmentation, which we call CPCP, which means the cut-paste class balancing technique. And then we use the standard object detectors. We use the we get the feature from the multiple head, which is for multiple resolution, capturing the multiple size of the objects. And then we get the features for each of the cells, apply the pooling to do the classifications for the each cells. And also what we did is that once we have these features, so irrespective of the cell, whether it is coming from the source or it is from the target, we try to we try to minimize the distance within the class and maximize the distance across the class. So this is something which is useful because we want to exploit the information that we have some few shots available. So we actually utilize those. So the underlying criteria here is that we want to minimize the feature distribution difference between the source and target. So we want to whether the images, whether the object is coming from the target or the source, we want to minimize the distance, and whether they are coming from the source and target, we want to maximize the distance. So here are some of the examples, some of the results where we compare with the lots of other methods, and we have a sufficient improvement in accuracy. There's again another data set. You can look into the details of these numbers in the paper, but this is just to show the recent results and something. So I showed you a couple of several of components, and we did the evaluation studies and found that these components are useful. These are some of the examples of the qualitative results. So this is the end. So it's kind of 2 years work. I just try to summarize in 45 minutes. It's very quick. So I will share this presentation with Amara, and you can share with the group if you want. So here's a link of the blood cancer dataset. We have released the code and the pre-trained model. If you have any problem in dataset or annotations or the code, please let us know. We'll try our best to update or try the feedback. And these are the codes and for the domain adaptation, and these are the links for the dataset for the malaria. Okay, thank you very much. And if you have a question, please let me know.
Thank you very much, Waqas. It was very interesting. So before opening the floor for questions, I would just ask our audience to give our presenter a virtual round of applause. And then if you have any questions, please go ahead and ask.
So I have a question. So it was
Sure.
thank you, Waqas, for this really informative talk, and tried to kind of uh, cover a lot of areas in a
Mhm.
very short time. It was a really, really nice talk. Thank you for that. So I
Thank
had
you.
one question. Like most of the data sets that you've collected are like, you have done the studies over there, and it's kind of limited to the demographic that you have. Like, and most of the systems are also built on the data that you have collected. Do you have any ideas on how you can generalize the model, or if it can be ported to some other demographic or things like that?
Yeah, thank you very much. It's an interesting question. So actually, but I know like like malaria, for example, to be honest, like malaria in Africa is different from the malaria in Pakistan or India and Bangladesh, for example. So, but this type of like malaria, which is Plasmodium parasite, which is very common in these and I mean a large part of the area, but not every part of the area of the world. So, I think that if you want to apply this model in Asia, it will works pretty well. But if you want to apply for the malaria model to the Africa, it will not work because they have different kind of mosquitoes and they have their different kind of life cycles and this and that. For the blood cancer, what I observe, what I heard and what I know actually, there's not much difference. So that's why we try to generalize those to the different resolutions and different microscopes. But I'm not sure actually that the blood cancer types and the cell types would be different in US than Pakistan. I have no idea. If you have some idea, I would love to hear from you actually. So, but I observe, I heard that from this lab that we are working with, they have said that they have bought some system from I think Sweden related to cancer, and then they observed that they thought that they originally thought that the blood and the tissues should be common in Pakistan and Sweden, right? Because they are human essentially. But they observed that these things were not working here in Asia, so they have to return it back. So for the malaria, obviously it will not work in Africa. The same techniques should work, but we have to change the data. For the blood cancer, this is an interesting question. I will look into details that like whether it's different in US or not.
Thank you for answering.
I have a question about data processing. And yeah, before that, yeah, a great talk and really nice to see all your work. So, I know like microscopy companies typically have like proprietary formats.
Uh-huh.
So for you, for the low cost and the high cost microscopes, like before doing your machine learning training, do you like convert it to PNG or do you have a specific format? And how do you go about handling that proprietary format from the different companies?
So actually, in our case, we don't have, I mean, that issue because we put simple mobile camera over the microscope.
Oh, sorry. Okay, I see. Okay, sorry,
So
I
this,
missed the start of the talk. Yeah. Okay.
yeah. So we wish like put somewhere here. I can show you the uh, yeah. So here we have some. So these we put the camera, and this also we use this microscopic camera as well that come with the company.
Right.
So that also save in the PNG format. So we
Okay.
use this.
Okay.
Yeah.
I see. So that HD 1500, they already have PNG output.
Yeah. Yeah.
Yeah. Thank you. Thank you.
Waqas, I had a question. You have high and low zoom images, right? So there should be a scaling difference, but you have like one-to-one correspondence.
Yeah.
So do you scale up or down? I mean, do you resample? Do you have to resample the image to get to that
No,
point,
actually,
or
what do you mean? Like, can you please repeat the question? So let me show you the image. Uh,
so?
okay.
Yeah,
So
so maybe in like high zoom, one patch shows like 1 mm by 1 mm, but in low
okay.
zoom, that patch would look like much smaller, or like the same size area would cover a larger actual area.
Yeah, you're right. So this is an interesting question. So for the high quality microscope, we have that. So let's forget about the image at the moment. So irrespective of the image. So the high quality, when we say the high cost microscopes, so the cost comes from three factors, which I know maybe somebody in the audience know better than me, but to me the three factors. One is the quality of lens, which is very good. Second thing is the area field of view, which is large field of view. And third is the knob things stuff. So because when we use a high quality microscope, they are very precise knobs to move around to see the stuff. But when the low quality microscope, you move the knob a little bit, it moves a lot. And so the same area captured by the low, even with the same imaging like mobile, so you see the same area, but in the low high quality microscope you see the big image. Okay, so when we put the mobile at the same location, if you see the first image here, so here this area is not in this image. So for example, you can this area is not in the low quality images. So we try to once we know the location, we go to that location and we try to capture as many cells as possible. And the size of the image is smaller in this case. And for the obviously for the training of the YOLO, because YOLO and the fast transfer and all these objective detectors take the standard size. So we for the pre-processing stuff, we just resize them. Obviously, for any size, but otherwise they are this of the actual size, and actual size is smaller than the high quality size.
Okay, thank you very much. So do we have any more questions? If not, I'll ask the audience to give our presenter another round of applause. And if you have any questions later, we can probably put you in touch with the presenter. Thank you very much.
Thank you very much. Thank you.